Good morning, Year 13s. Right, welcome back. Nice to almost see you again. Unfortunately, I'm going to have to miss this week of school and last week actually with you because I'm trapped in quarantine. But I am looking forward to seeing you guys in person. So, all we're going to do this week is two online lessons. So, just like what you were used to during the lockdown and stuff. And yeah, we're going to be able to rock on from there. So yeah, I'm super excited because I get to teach you guys mechanics this year. Mechanics is the best, most awesome one, and yeah, I'm pumped to teach it, and hopefully you're excited to learn it as well. Not that we didn't love algorithms, of course we loved algorithms as well, but this is mechanics, so how much better is that? Anyway, okay, so what I gather is during the 5 week plan or during the online lessons, you guys have already started and done a lot of the moments unit. So I was just going to make sure that everyone gets that and use our first lesson just to make sure you understand the basics of moments and equilibrium. Okay, so that's what we're going to do today. So I've only got two questions for you because I think Dr. Proud told me that you have done this before with him, so I'll try not to be too slow and I'll give you just one question of each sort and then I'll set you on your way. So there you go. Cool. So first things first, moments in the book is just this here. I think you can see my clicker. Yeah. So moments is just this. Is moment equals FD. That's what your book calls it. Now that's weird because in the year 13 regular maths book, as well as in this year 13 further maths book, they didn't give it a variable in any of the cases. So I have a variable that I've used ever since Canada because moments can actually be called torques as well because a moment is kind of a twisting force. It's actually a force directed at a distance. But if you consider the effect of that, say on a bolt or something like that, if you were trying to tighten something on, they call that torque in real life, which I think that or in engineering, I should say, in shops and stuff like that, they'd call it torque. And it's got the Greek letter tau as a variable. So I'm going to use this as my formula. Moments, or torque, is equal to force times the distance. The S is the same S from Suvat. Now, we'll go into this a lot more later, but the distance is actually the perpendicular distance to the hinge. Okay, so this is what it's actually technically called, is the shortest possible distance to the line of action of the force. Now I'll tell you what a line of action is. See this 3 newtons here? If you continued that line on forevermore up this way and forevermore that way, the shortest distance is actually the 0.4 because it hits it perpendicularly. The infinitely long red line. I'm even going to draw it on. You don't need to know this yet, but you will in a couple lessons. So if I even drew it on like that and along like that, perfectly straight line. That perfectly straight line is called the line of action of the force. Now let's get rid of that. That's horrible. Okay, now you're going to be really ace at this, so I'm going to try to go quick. Here's what the question says, the first one. It says the situations below involve several forces acting on each object. For each one, find out the total moment. So that means like the total overall torque. Now, I might do this in an unusual way, but have a little look. You can do it the way that you're used to. If you've done this before with Dr. Proud and you really got your head around how he did it. Hopefully he just does it the same as me, I'm not sure. But I know I teach this a little unusually, but let's do it anyway. Okay. Just like when you do like forces, how you do like a balance equation, you have like the forces up equal the forces down, or the net forces equal something. We're going to be doing this. It's a net torque equation. Now here's what I'm going to do to start with. I'm going to decide a direction to be positive. Now the two directions you've got when you're doing moments, or torque moments, is you've got clockwise around like that, and anti-clockwise around like that. Cool, cool, cool. Now what you're going to do then is you're going to pick one of those two directions to be positive. So I'm going to pick clockwise to be positive because why not? So step 1, clockwise is positive. Shabam. Cool. Step 2, I like to do it this way. I like to do what's called a net torque equation or a net moment equation. So here's what I'm going to write. T net, because that's the overall, like kind of like if some of you have part-time jobs, you get like your gross pay or whatever. It's how much you get paid, but then you don't get to keep it all because you pay taxes and you pay other bits and bobs out of your pay, and that's called what you net, and net's what's left over. So it's the same kind of net as that. It's what's left over. Cool. So clockwise is positive. Now, I said that, if you put your finger at O here, it's hard to show you with my mouse, but yeah, put your finger at O, which one would go clockwise, the 3 or the 1.2? That's right, it's the 3. So the formula for moments, my lovelies, is force times the distance. Force times distance. So here we go. It's going to be just this. It's the force, 3 times the distance, 0.4. It's all in meters, it's all in newtons, we're good to go. Cool, now that's clockwise, so it's positive. Now the other force, though, the 1.2, it's anti-clockwise, which means I'm going to account for that simply by using negative. So minus, and then it's the force 1.2 times the distance of 1.4. And that's all you've got. So what do we get as our final answer there? T net. Bish bash bosh it into the calculator. Now, I would never just cheat and do this ahead of time and have it on a piece of paper ahead of me. So let's just do tick, 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 tick in the calculator. Oh yeah, and you should have got that it is negative 0.48. Now, if you did negative 0.48, that's kind of bizarre, because we just got a negative. Oh, I should say as well, it's force times distance. The unit isn't a unique unit, it's just the Newton meters. Cool, so it's negative 0.48 Newton meter. Now that's weird. What does that actually mean in real life? Well, if it was negative and clockwise is positive, it just means it's in the anti-clockwise direction. So your answer, which you should actually put, is this one, Newton meters, but then define that actually it was around that way. So I got a negative answer because I picked, maybe on purpose, an incorrect direction to make positive. So I knew that this one was bigger, but I still picked the other one just so you guys could see. But that's kind of what the answer is. Boom, you've got your net moments. This thing, if it was, say, an object in the middle, say it was like a peg or something in the middle, it would be spinning around this way. It would spin around anti-clockwise, so it wouldn't be in equilibrium. Cool? Okay, harder. Bang. Oops, bang. There we are. Okay, a little bit harder now, my lovelies. These are the hardest ones from kind of regular year 13 maths. Maybe not quite the hardest, but getting there. And these are equilibrium questions. So I'm hoping that you guys realize equilibrium means that the forces are balanced, okay? For something to be in equilibrium, it could either be the thing is not moving. So if you think about your calculator set on the table in front of you, that's an equilibrium because the weight of the calculator pushing down is balanced by the reaction force of the table pushing upward. So yeah, that's equilibrium if something's not moving. And similarly, you can have equilibrium, say, in a car where something's moving at constant velocity. So it's where the forces are balanced. So when you're in a car, you don't always feel pegged back to the back of your seat unless it's like one of you guys driving and you're driving really, really aggressively. Normally, in most people's cars, you sit kind of normally and it feels normal, like you're sat of something that's not moving, because that's equilibrium as well. If something moves at constant speed, it's only not equilibrium if something's accelerating. So woo, it's been an ages explaining this, but yeah, after I said I wouldn't. But here we go, let's just solve it then. Uniform plank AB of length 1.2 meters and mass 5 kg carries two particles. One of mass 2 kilograms lies at C, and one that is 40 centimeters and 40 centimeters from A. The other is at B and weighs 1 kilogram, so that's that bad boy there. The plank is supported at A and D, and blah, blah, blah. It just gives away, it tells you what's in the diagram, essentially. And find the reaction forces acting on the plank. So to start with, you got to think, what's a reaction force? Well, a reaction force is a contact force. So essentially, the beam is the subject of the thing that we're dealing with, the orange beam there. And so it's got 2 points of contact at A and D. Those are the two reaction forces that it's on about. So you guys ready? Here you go. If you're doing mechanics with me, the first step is always, always, always draw a picture. This picture isn't suitable because this picture isn't a free body diagram. So we are going to make a free body diagram to begin with. So you kind of have a skeleton anyway of what it should look like. So just have a little sketch with me. There's our beam, like that, beautiful straight line beam. It's resting on A, which is exactly at the edge. Beautiful, my amazing art skills. It's resting at A. It's resting also on D, which is there. There's D. It's got two little doodads on it. It's got C there, and it's got B at the very end, and there are the masses. Cool, cool, cool beans. Let's put on some distances as well. I'll do that in green, I guess. So to C, it's 0.4 meters. So it looks like we're copying the picture, but you'll see why we have to do it in a sec. The entire beam is 1.2 meters. Beautiful, there you go. And D to B is 0.2 meters. 2 meters, boom, and shaboom. So we are getting there. I'm just to color that in a little bit. Okay, the reason why we draw this is we want to do what's called a free body diagram, which is a picture that shows every single force acting on the object. And our object this time is the beam. So tell me, if you were the beam, what would you feel? Well, to start with, you've got a weight attached to you in the middle here, C. So I'm going to draw a straight line down just like that, and because that represents the force, don't forget, from year 12, and that represents the weight of C. Now, I know lots of you will have put, what does C weigh again? C is 2 kilograms. Lots of you will put brackets 9.8. That's fine as well, but I like to do it algebraically, so you're going to have to deal with that, haha. So, yeah, that's cool. And then at B, I'm going to call that WB, because that's the weight of B. And what else have we got? Well, it's resting on A, so there's a contact force there, because it's normal contact force. Do you guys remember what letter we usually use for that? That's right, it's R. So we have RA. R, I think, probably because it's a reaction force. Yeah, because it's called the normal contact force, which doesn't really even have an R in it, unless it's normal. Yeah, but anyway, it's an R. I think it's because it's a reaction force. That's probably why they chose that letter. Here we go, and this bad boy here is RD. So there's all of our forces acting on the object. Or is it? Is there anything I've missed, my lovelies? Anything at all? Oh, that's right. Our plank itself has a weight because it's a uniform plank, which means it's even throughout. And it has its own weight. So it also feels its own weight. So here we go. Because it's uniform, it's going to be exactly halfway. I'm going to call this WP for weight of the plank. And it acts at a distance of 0.6. Because, oops, that was red for some reason. It acts at a distance of 0.6 meters. Bish, bash, bosh. So there you go, guys. Absolutely beast mode. That is a free body diagram, and it's beautiful. Cool. Find the reaction forces. Okay, so this is like a tricky one from moments, but let's do it anyway. I'm going to do moments in purple. Let's treat ourselves. Here we go. Okay, first things first is when you do a moments question, I'm going to scroll right down to here. You need to decide where the hinge is going to go, and you're allowed to put the hinge wherever you want. So I'm going to put it at A, and I'll tell you why just now. So first thing you'll write is hinge at A. Cool? Now, why would I put the hinge at A? Well, and I'll even draw a cross there. Oh, shoot. Here we go. Let's get that. Okay, hinge at A. Why would I choose there, you might be thinking? Well, remember, there's two forces that we want, RA and RD. If I put the hinge at RA, the distance to RA from the hinge is 0, which cancels that variable, which means that the only variable I'll have is RD, which means I can solve it because it's an equation with only one unknown. So here's what you're going to do next. You're going to here. Because it's an equilibrium question, I like to think of it this way. The thing's not rotating, right? So all of the anti-clockwise moments are going to equal all of the clockwise moments. Cool. What's going anti-clockwise? Well, it's RD. And what's the distance to RD from the hinge? Well, it's going to be a distance of, and I'll show you with my mouse, to get from here to here. Well, it's 1.2 all the way, less this 0.2, so it's at a total distance of 1. So grab your pen and put 1. Grab your pen again, then push 1. There you go, okay, so that's what we've got for anti-clockwise. The rest of the three go clockwise. So WC to begin with, just because it happens to be the first one. Well, how much did C weigh one more time? C weighs 2 kilograms. So the formula for weight, don't forget, the formula for weight is equal to mg, right? So here we go. The weight of it's 2. G is always 9.8. And since the formula is Fs, the distance to it is 0.4. Cool? So it's this, yeah, hopefully that's okay. Plus, let's do the Planck next. The Planck weighed 5, I think I remember it being 5. The Planck weighed 5, yep. The Planck weighed 5, I'm just going to leave it like that actually. The Planck weighed 5, G is always 9.8, and the distance to it is 0.6. Boom, because it's that distance, yeah, from the hinge to it. And finally, the one more clockwise one that we've got is WB. So here we go. WB weighed 1, it says, times 9.8. And then that is total distance, this time, of 1.2, because it's the entire length. So can you see how this picture really, really helped me in this regard to figure out where everything was? So boom, boom, boom. This now, my lovelies, is just a really nice, easy equation. You don't have to show any more steps than that. Go right to the final answer. So obviously on the left-hand side, it's just going to be RD, because that's the reaction force at D, and timesing by 1, it stays the same. And all of these bad boys together, type it into your calculator. I wouldn't have done this ahead of time, so boop, 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 calculator. And you should have got 49 newtons. 49 newtons. Oops, my Newton is rubbish. Okay, 49 newtons. Cool. And that's it. You've answered half the question. So it wanted to know what the reaction force at A and D was, so you're supposed to do them both, but you now know what RD is, so hooray, we're flying. Okay, now here's the thing. I might say to you right now, how will I do RA? So have a little bit of a think. Ready? Think. Okay, and now that you've had a chance to think, I'll bet you a lot of you said, well, what we could do is just do it the same as the last time. We could move the hinge away from there, and then put the hinge here, and do the same exact question again. You're absolutely right. That would totally work, but it's a little bit harder than it needs to be. Because if you consider it, well, yeah, so if you did it that way, and you're doing it that way, carry on, good work. But there's something weird with this. If you think of it, we have 1, 2, 3, 4, 5 forces. We're also given this thing isn't moving, it's in equilibrium. Of the 5 forces, I only just don't know this one, RA. So instead of using moments, we can actually scheme this a little bit, and let's use forces instead. So are you ready? Let's do forces instead. So if I'm not the one who taught you mechanics, this might seem a bit weird, but I'm going to use a net force equation instead of a moment equation. So here you go. First things first with forces, define what direction you're working in, vertical, because all of our forces are up and down. Which way do you want to be positive? I'm going to say up is positive just because RD is up, and that's what I'm solving for. So here's what you do. F net, the overall balance of the forces, is going to be everything up, which is RA plus RD. Take away everything down. Take WC, take WP, take WB. Cool beans? Right. Now, I know that you think that F equals MA, but F doesn't always equal MA. It's actually quite a specific one you get to substitute MA in for. It's the net force, F net, that equals to MA. Because it's not accelerating, it's going to be the mass times 0, which means 0 net force. Cool, cool, cool. Look at this schemey way of doing things. So here's what we've got then. 0, oops, it's red again. 0 equals RA, which is what we want, plus RD, which is what we know, 49. Ditch the newtons in the calculation. That just makes things complicated. Take WC. C was the one that weighed 2, I think. So it's 2, 9.8. And I don't need the distance this time, right? Because I'm just doing regular weight, which is mg. I'm not doing force times the distance this time. I'm just doing regular old force. Take the weight of the blank, 5 times 9.8. Take the weight of the at B, which was 1 times 9.8. Guess what, guys? Have a little look at it. You've only got one variable in here, which means bish bash bosh it into your calculator. You don't need to show any more steps. There's no points for working out in this, really. There's points for complicated workings out, but this is just like mechanical. So when you get that all the way through, boop, 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 in your calculator, 29.4. 29.4 newtons. So if you got that, you've got it absolutely right. And I hope that you've got that. So I would say this is kind of a standard level tricky one from regular A level. I think our further maths A level is going to go a little bit harder with mechanics, but yeah, cool beans. So hopefully that's okay for you, and I hope that you're flying. Cool. Right, so here's what I'm going to get you to do. I just want you to try this from your brand new snazzy purple, I think. Yeah, purplish bluish book. Page 80, question 2, 3, 4, 5, and 6. And that's all I want you to practice. This one's not going to be homework because I will do one more lesson with you this week. And I'll set a homework based on that one because it's a little bit harder than this topic. But I still want you to have a little go at that today. And if you have time in Newport Study or wherever the devil you're allowed to go with quarantine these days or with self-isolating these days or whatever is happening at the school. Oh, I miss being in the school. Yeah, and try to finish them wherever you can, I'd say. And that's it. You don't have to upload anything. You don't have to leave me a comment or anything. The actual homework is going to be coming later on this week. Cool, guys? Right, well, see you soon. I hope that was okay. Email me if you have any questions, or better still, leave me a comment on Show My Homework if you have any questions. And talk to you soon. Bye, buddies!